So in the last video, we discussed the difference between delta G standard and delta G. And delta G standard referred to when things were under their standard states, their standard state conditions. And that meant for gases, we were under pressures of 1 atmosphere. And if you were a solute, you were under a concentration of 1 mole per liter, otherwise you were pure. However, we're often not under these standard conditions, so we have to use delta G in order to calculate what will happen under those conditions. And the equation we saw last time was delta G is delta G standard plus RT times the natural log of Q, where we said Q was the reaction quotient. Now, Q technically is a thermodynamic reaction quotient. And it's kind of interesting, actually, because the thermodynamic reaction quotient, and how do you know you've got a thermodynamic one? Well, you've seen QC, where we use concentrations. We have seen QP, where we use pressures. And it turns out that when we have Q, that is the thermodynamic one. And it means that when we're dealing with gases, we use pressures. And when we're dealing with solutes, we use moles per liter. And so we mix and match. So, for instance, if we had a reaction that, oh gosh, I don't know, somehow involved, the 2 chloride ions, okay, converting to chlorine gas, plus a couple of electrons, then we would write the reaction quotient for this as the partial pressure of chlorine gas divided by the concentration of the chloride ion squared. Okay, we would also leave off the units. If you wanted to, you could remember to divide this by 1 atmosphere and divide this by 1 mole per liter, and it would essentially make it unitless. It would be more proper, but normally what we do is we just leave off the units and calculate it otherwise. I'm not exactly sure what we do with those electrons. I'm not really sure if we're supposed to put them in or not, so that's probably a bad example. So let's go to our water evaporating now and see if we can predict whether water will evaporate at room temperature to a vapor pressure of, say, 0.01 atmospheres. So what we're going to do is we're going to calculate delta G for this reaction here. So since we're not under standard conditions, then we're not allowed to write that little standard symbol there. How do you know we're not under standard conditions? Well, we're not under 1 atmosphere of pressure. All right, so we can go ahead and we can calculate that. So delta G is delta G standard plus RT natural log Q. Now, delta G standard we saw in the last video, we didn't actually calculate it, we just simply stated it. It's positive 8.59 kilojoules per mole. And you can get that a bunch of different ways. So the easiest way is to probably just go ahead and look at delta G of formation of the product, so water vapor, and subtract away from that delta G of formation of the reactant, the liquid water. Okay, and those are under standard conditions, so they would officially apply to pure liquid water and water vapor under 1 atmosphere of pressure. So we got 8.59. So the take from that is that this reaction cannot occur under standard conditions. But we're not making 1 atmosphere of water vapor, we're making 0.01, so it's much, much smaller. So maybe that makes it more favorable. So let's go ahead and calculate and see. So we've got RT, so R is 8.3145 joules per mole Kelvin. Temperature is 25 degrees C, but we got to convert to Kelvin, so that's 298.15 Kelvin. And we got to take the logarithm of Q. Now, what is Q? Q is the reaction quotient, the thermodynamic reaction quotient. So since we got a gas on the right-hand side, that is the vapor pressure of that gas. And we got a liquid on the left-hand side, so it has an effective concentration of 1. So we just measure it in atmospheres. Okay, remember we leave off the units, or if you like more properly, when we write the pressure of water, what we really mean is the pressure of water divided by the standard pressure of 1 atmosphere. And of course, all that really does is removes the units. So now in our expression here, we've got the natural log of 0.01. Didn't leave myself enough room. And when we go ahead and we calculate what we get, delta G now is negative 2.8 kilojoules per mole. So we look at that and we say, it's negative, so that gives us a green light, so the reaction can occur. Water can evaporate and form 0.01 atmospheres of pressure. In fact, because that's still negative, it could evaporate and make a little bit higher of a pressure, and eventually it would form a pressure where delta G was now 0. It would be at equilibrium, and we'd see that would correspond to something like, I think, 23.8 millimeters of mercury. So yeah, it's spontaneous, so it's not our imagination. Water can actually evaporate when we spill it on the ground or spill it on the bench top.